We left off talking about the first law of thermodynamics. Now, underneath that, Roman numeral 1 is A, standard state. Now, we are back to taking notes on our own instead of me having them given out to you, just filling in the outlines. So you kind of have to keep them organized for yourself. But my notes are organized. They do make sense if you look where they are. Every now and then I'll have something that's out of place for some reason. We have to do things differently, but this should go right underneath thermodynamics. First law of thermodynamics. All right, now look at. Here's the thing. When you're talking about, we're about to start, up till now, and including the 2 labs we did, up till now, we have talked mostly about physical changes. All right, think about it. We took hot water and cold water on Friday, predicted the final temperature. The day before that, we took hot metal and cold water. We predicted the specific heat of the metal. Okay, these are just physical changes, how hot I get the water, how hot I get the metal, put them together, see how much energy is absorbed or released in a physical change. We're going to start now talking about, remember where we're going with this. Our goal was, and I'll say it again, find out whether a reaction can occur or not. If I take sodium and I add it to chlorine, does it really give me sodium chloride in a spontaneous reaction or not? That's the question. I want to find that out. Now, we know it does. We've seen it. But I have to be able to predict that because I could take any element or any compound and say it's going to react with somebody else, but that doesn't mean it's going to. Now, in order to do that, I have to first talk about what state these guys are in. Because remember, every one of those elements of the periodic table and almost every compound I can have exist as a solid or a liquid or a gas. I mean, not really. I mean, some of them will decompose first. But I can, depending on the temperature, change their state. And they will react differently. Not only that, some guys like carbon exist in more than one state. Remember? Diamond, graphite. So I've got to be very specific. So that's why today, and this is going to be a very short class, and then you'll have some time to work on some problems. And then we have a double period today. The next part, we'll talk about, we'll take this somewhere. So we're going somewhere with this. The point is, I have to talk about standard state first. What state does the element exist in by itself, normally? That's what I'm talking about. The most stable state of a substance at standard pressure in 25 degrees Celsius. Notice, normally we talk about 0 degrees Celsius, but here we use 25 because we want room temperature, basically. That's where we work. We don't work at 0. Okay, we don't work at freezing point of water. That's why we use 25. So I got to know what state these guys are in. If I use a different state, water is a great example because it exists in all 3 states. It's going to have a different amount of energy associated with it, which makes sense. And that's why I told you better have your books today because you're going to be looking in the back of the book to tell me what's the standard state. Some of them, the elements, you can tell by looking at the periodic table. It's that easy. What is the standard state of all the yellow ones up there? Solid. What's the standard state of all the green ones? And the only pink ones up there, there's only 2. There's that one, and mercury is liquid, right? Okay. Hydrogen then would be what? A gas, right? But be careful. I purposely chose hydrogen. What? Can I just put Hg? What is hydrogen? Also from last year we know. Diatomic, remember? Remember the diatomic elements, Brinkelhoff? So it's H2 gas. So you have to remember that too. Diatomic elements, allotropes like carbon, and then the 3 possible states. What about carbon? Speaking of carbon, there he is. Now, how am I going to know what's the standard state of carbon? That's where you got to look up in the back of your book. Okay, open up the back of your book to Appendix K, I believe.
We need bigger desks.
Let me see your Appendix K. Make sure that's the right one. I think it's Appendix K. Thermodynamic values, is that what it says? Yep, that's the one.
Where did you find that at?
Appendix K.
Are they going in alphabetical order?
No, they go all over the place. A, X, L, J, you know.
I don't. Okay, wait, let me show you. Hold on.
Don't you know your ABXs?
Okay, sorry. No, I just said my alphabet.
That's exactly right. All right, anyway. Now, everybody find on there because you know what? I'm going to tell you this right now, and I'm going to remind you of it I don't know how many times. You know what? One of the biggest mistakes you're going to make, the stupidest mistake. By the time we're done with this chapter, you're going to have to use every one of those columns. Okay, every one. What's the biggest mistake? What's one of the biggest mistakes people are going to make?
Taking this class.
Taking this class. Okay. Austin finally had a good one, and it didn't involve the word anyway. Look on the columns there. One of the biggest mistakes you'll make is just looking in the wrong column. It's very easy to do. Find carbon on there. Okay, which one do you think is a standard state? Look at the value for the delta H of him. For each of them. Which one do you think is a standard state of carbon? It will be the one with no energy associated with it. Graphite. You see why? Everybody see graphite? See the 0 next to him? Look throughout that column, that first column. Do you see zeros anywhere else? No. The first column, vertical column.
Yeah, it's at the top of.
There's a lot of zeros, aren't there? Okay, anywhere you see a 0, that tells me that that guy, here's what that 0 means. Look up here. It means no energy. 0 energy is required to get carbon into that state. Notice, if you look up hydrogen gas, notice it's a 0. There's no energy required. There's no energy given off. It just exists like that. So carbon graphite solid is the actual standard state of carbon. We have to use the standard states in doing the next thing I'm going to show you next period. All right, called the actually I guess it'd be this period, the molar enthalpy of formation equations. It'll still be right now. I'm going to show you that. I have one more of these to do. Some guys are ones you don't know about yet that are also allotropes. Phosphorus is another good example, and you will see him in the future. I have a neat little demo on. It's a video actually. I can't show it to you because phosphorus is nasty stuff. I have a neat little demo of what happens to the 2 different kinds of phosphorus. One kind of phosphorus, I open a jar, let it sit around the table, no big deal. The other kind, when exposed to air, bursts into flames. Okay, so it's very nasty stuff. That's weird. So and they're both phosphorus. They're both pure phosphorus. P4S phosphorus or white phosphorus is the actual standard state of phosphorus. And you see why? Look on your column there. It should be a 0 next to him. Okay. You will need those in a second. You can probably put them on the floor for a minute while we give you the rest of the notes here. But do keep them open to that page. All right. Now, how are we going to use the standard states? First thing we're going to learn how to do today is how to write what's called a molar enthalpy of formation equation. In other words, I want to know if I were to take the standard state elements and make a compound. And I always talk about, what's my classic example? Sodium plus chlorine equals sodium chloride. I want to know if energy is absorbed or released and how much of it would be absorbed or released. That's what the molar enthalpy of formation equation means. Okay? It's the amount. I want you to listen to this definition because a lot of times people just get confused by the big words. All right? Here's what it's saying. I'm going to make water, for example. I have to take hydrogen and oxygen in their standard states, smash them together and make water. To make salt, sodium and chlorine. To make any compound you could think of, sugar. It'd be like making sugar from carbon, pure hydrogen, and pure oxygen. Now, we don't do that. No one makes sugar. But no one makes salt this way either. We don't make salt by reacting sodium and chlorine together. We dig it out of the ground. All right? We don't make most of these compounds from their standard states, but I have to know how much energy is given off in order to be able to do the rest of the calculations. All right, so do this. Write this down as my definition. It's the heat absorbed or released when 1 mole of a substance is formed from its elements, its constituent elements in their standard states. And I'm going to show you how to do that with a couple examples and I'm done. Okay. Now let me show you an example of this. If I ask you on the test, and the weird thing is, I'm going to go beyond this. We're going to do so many more difficult problems in this, that people often, when it comes to the test, leave this blank because they completely forgot about it. I don't end up after today doing a whole heck of a lot of these. All right, but they are kind of important because they're the basis for everything else that we're going to do. All right, there's my example. There will be one on the test like this, and I have, of course, some homework on it tonight. But people often, because we get into so many more problems we're going to do after this, like I said, that's one of the reasons if I do have a midterm, I would like to wait till thermodynamics is over. It'd be nice if I don't have to give it before the end of this marking period. Because I know this chapter will not be over in a week and a half. We have a lot to do. Or if it is, it'll be barely over, and I won't have time to give it anyway. I don't really want to stop in the middle because you forget things to begin with already. Okay, so you know what I'm going to do. I use sodium chloride as an example. I use water as an example. Here's carbon dioxide. If I were to make carbon dioxide from its constituent elements, in other words, I would have to basically burn carbon graphite. Burning graphite would be raising the temperature enough to combine it with oxygen, and that's what I would get. So what would the equation look like? Kind of like this, wouldn't it? C, solid graphite, plus oxygen gas yields CO2. Now, this last number over here, you would only get by looking where? Yeah, look at your back. That's why I said you keep the books open. Look up CO2. Notice what the value is. Sorry, the sign of that guy is, not just the value. What does it say there, Bree, in the book for CO2 gas? What's his value for delta H? Negative 393.5. Why do I have a positive up here? What does negative 393.5 mean? No. It's releasing. It's exothermic. So if it's exothermic, I write in, anytime you have a negative value, it means it's exothermic, it's releasing energy, it gets written as a product. You see what I'm saying? That makes complete sense. In other words, let's read this as if you were reading a sentence. Here's how you would read this. Carbon plus oxygen, carbon reacting with oxygen, gives off CO2, and it gives off 393.5 kilojoules of energy. If that value were positive in the book, where would it be here? On the other side. Exactly. That would say it was being absorbed. You see what I'm saying? Let's do one more example, all right, a little slower, and I'll do it with you because that was a pretty easy one. This was so easy for a couple of reasons. Also, notice it did not need to be balanced, right? Okay? We didn't even think about that, but it doesn't. One carbon, two oxygens, nice and easy. Copy that question down. And we'll do this one, and that'll be my last example, and I'll give you time to work on some problems. This one will illustrate what happens when I have to balance things. All right, let's see if we can do this. Actually, no, let's see if you can do it yourself. Because I think there's a mistake you may make. Try that on your own first, then I'll do it on the board. Look up the standard state of hydrogen. Look up the standard state of chlorine. Put the two together, and the mistake you're going to make, I think, at the very end. You won't even realize it's a mistake. As a matter of fact, it wouldn't be a mistake, but for the fact that this is the molar enthalpy of formation. You all put those two guys together, right? No problem there. You know the formula for hydrochloric HCl, hydrogen chloride. Okay. And so everybody would write that much. Geez, this seems like it's awfully easy. But then you got to balance it. Most of you probably balanced it with a 2 right there, right? And that would be right, except for one problem. Let's read the definition. It's the amount of energy or heat released or absorbed when 1 mole of a substance is produced. So you can't very well use that value, it's in the back of the book, and have 2 moles produced. So you're going to do something very strange here, something I would never have told you to do in Chem 1. All right? You're actually going to put a half here and a half there. That will give you 1 mole, 1 up there, right? And some of you are probably looking at that and saying, but that's impossible. I can't have half of an atom. I can't have half of a hydrogen or half of a chlorine. You're right. I can't have a half of a person, but I can have a half dozen people, can't I? That would be 6. I can't have a half a hydrogen, but I can have a half of a mole of hydrogen. That'd be like a half a dozen hydrogen atoms. These are hydrogen molecules, right? So that's what that means. Now, by the way, what's the value in the back for HCl? Positive or negative? Negative. So he will go on this side, plus 92 point, what is it? 31 kilojoules. And you're done. That is the answer. That's the final answer. Okay? All right. I want you to look up, while the tape is still rolling, I want to actually say this to anybody who was absent today. Your homework's going to be on page 637. Open up to that page right now. I want to read one of the questions for you to show you why this is a college text and what that means for you in the future. One of the things college texts take into account or take for granted is your vocabulary and reading abilities. Okay? So we look at this guy, and I read him. Well, first I need my glasses. I want you to look at number 26. Okay, everybody looking at 26?
Yeah.
Okay. Write the balanced chemical equation whose delta H of formation reaction value is equal to the delta H of formation reaction for each of the following substances. Now, that's just an ugly way of saying write my molar enthalpy of formation equation for those guys, okay? The book is often going to do this. Write things as badly as it could possibly think of. The other questions you have for homework tonight are 24 and 25. And again, all I want there is, it seems, again, what exactly is it asking me for? Just tell me what's the standard state of these guys. So like say 24A. You know what we're going to write for 24A? Cl2G, gas. That's it. Cl2 gas. Okay? So it's very short homework. Your homework is 24 to 27. I'll write that on the board in a minute.